Welcome, everyone. First announcement, homework one solutions are up on EdSTEM. So you should be able to access them under the lessons tab, along with all the other solutions that are already up there. And as a reminder, so we don't have weekly homeworks. The homework schedule is up on the website. Homework 2 will be posted this coming Monday. Okay, so they're kind of spaced out so as to cover more as our course gets more intense. They become more frequent. Okay. All right. So last class we talked about circuits. We saw the limitations of circuits. Then we came across the important concept of universal circuits. What makes general purpose computing possible? If you had to print down a circuit, just do one circuit, and that's all that you need. And then we talked about one of the most important limitations of circuits, which is that they're only able to handle inputs of a fixed length. It doesn't matter how big your current input length is. Eventually, in a few years, you are going to go beyond that, right? But as we said at the very beginning, our goal in this course is to kind of come up with models or see if it's even possible to come up with a model which can transcend, our immediate hardware constraints or whatever you have, right? We want to build something time-proof. And to that end, we started talking about, one of the very simplest class of algorithms there is the class of single-pass constant memory algorithms, right? Another way to phrase that is deterministic finite automaton. So you have a machine kind of has a figure around in that after reading a single bit. Okay. We saw some example of that in the last class. Today, what we'll do is look at other examples, kind of play around designing DFAs for various tasks, and then look at various operations on DFAs. Okay. We're always talking about meta computing, right? You have a circuit, and then you do something with the circuit as an input for something else, and so on. Okay. Hopefully, by the end of this lecture, you'll go around your day-to-day life and see which tasks can be computed by DFA and which tasks cannot. You can maybe come up with one example each or something. That'd be very nice. Okay, so let's look at another simple example of DFA, and then I'll kind of connect to other literature and other notations that you come across them in various other classes you might have seen. Okay. So this time I'm going to do it in a slightly different order. I'm going to define the DFA and I'm going to draw it. And I want you to tell me what it computes. Okay. So one nice thing about DFAs is often, by staring at them, it's easy to check what they're computing. Okay. Often, not always, but, at least the example that we are going to see, that's going to be the case. So we have 3 states. Maybe it's just easier to do it this way. Okay, and we call them 0, 1, 2. You see a 0, you stay there. You see a 1, hop across. You see a 1, you hop across. 0, stay. 0, stay. 1. Okay, and the start state, sorry. The double circle, as I said, kind of identifies the accepting states or the special set S, which tells you whether the function outputs 1 or not. And even though it's not strictly speaking necessary for the notation that we have, the single arrow without any origin kind of points to the start state. It's not strictly speaking necessary for us because of the convention that we're going to use, which is that 0, the state named 0 is always the start state, but you can always point to it. Okay. And if you were to write down the transition table, you can write it down too. I'm just going to write a couple of entries. Diagrams are good, but if you had to formally define it, then it should always be the transition table, right? So transition table the transition function takes a state, a bit as input, and then outputs a state. Right? So here, for instance, we have 3 states and 2 bits. So you get kind of yeah. So let's say you have 0, 1, 2. What happens if you see bit 0? 0, 1, 2. What happens if you see bit 1? Okay, if you're in state 0 and see 0, you stay at 0. If you're at 1 and you see 0, you stay at 1. The same thing here. And here you kind of jump across to the next step, next state, sorry. Okay, this is the transition table. And this is T, S is 0. Okay, so what does this function compute? What function is computed by this automata? So D of X is 1 if X satisfies some property. What property should it satisfy? Exactly. Oh. Someone was asking, did Scribble disconnect? Hopefully not. Okay, I think we're back. So if X is 1, if number of ones in X is divisible by 3 and 0 else. Okay, essentially, like, for every 1, you kind of jump to the next state, right? And once you see 3 ones, however space they are, you kind of come back to 0, right? So the state is meant to indicate your reminder of the number of ones after dividing by 3. Okay, and the starting state and the accepting state is 0, so you only output 1 if the number of ones is divisible by 3. Okay. And just for once, let me also kind of, tediously work out one example of what happens when you run this DFA on a specific input. Okay, so let's say I run it on the input 0, 1, 1, 0, 0, 0, 1. Okay, and so what happens to the states? State transitions. Okay, so my starting state is 0. I see 0, so I stay at 0. Okay, so this is current state. Okay, I'm kind of showing how is the memory being updated, right? So I see the bit 0, I stay where I am. I see the bit 1, my state changes to 1. I see the bit 1, my state changes to 2. I see 0, I don't go anywhere, I just stay where I am. Okay, and finally I see 1, and then I jump to 0. Okay, these are the sequence of state transitions that the DFA goes through on this input X. Okay, you can give however long an input you want, it'll still give you some answer in the end. All right, any questions? What if I ask you now to design give me a DFA that does the following. So D of X should be 1 if number of ones in X is 1 mod 3 and 0 else. Okay, so I wanted to output 1 only if the number of ones in your string is a multiple of 3 plus 1. Like, either it has 1 1 or 4 1s, 7 1s, 10 1s, 13 1s, and so on. How can I do that? Any suggestions? Yeah. Exactly. So in this case, at least, the only thing that we need to change is the set S of accepting states. Okay. So let me copy this diagram. Okay. So I change the accepting state, and then it changes my function to something that outputs 1 only when the remainder upon dividing by 3 is 1. Okay. So it's kind of a simple change to the function. Any questions about the definition of DFA? Yeah. So the double circle denotes the set S. It's our shorthand for what the set S should be. Okay, and remember the set S is important in the definition of DFA because that kind of determines whether the function whether the DFA says 1 or 0 in the end, right? So you read the entire string, you end up at some state. If the state is an element of the set S, you output 1, otherwise you output 0. Okay. And this double circle is kind of our shorthand to pictorially denote which elements are in S. All right. So you can think of it as, okay, I'm hopping around. If I end up in a state which has a double circle around it, then I output 1, otherwise I output 0. Okay.
So the output is never explicitly drawn, it's just inferred.
Yeah, I mean, the automata is fixed, right? But the input is arbitrarily wrong, so we cannot draw it. Okay. Any other questions? Okay, so we'll see some more examples. And then I'll say some remarks about thing. So let's do another example. So let me call it example 4. Okay, so here's a function. And I want the function that I'm interested in computing is, again, kind of a very simple function for the time being. It should output 1 if the string X ends in 1 and should output 0 otherwise. Okay, you're reading the entire string, but the only bit I care about is the very last one. How can I write is there a DFA which can compute this function? Okay, let me get you started. I'll draw the start state and then put the dummy arrow. Now you tell me what to do. Yeah.
Whenever you see 0, you go to 0. Whenever you see 1, you go.
Okay, so let's see. So if you see a 0, you just stay here. If you see 1, then you go to the next state. And if you see 1, you stay here. If you see 0, you go back.
And there should be a double circle around 1.
Yeah, so 1 is the accepting state. Okay. So essentially what you're doing is think like a finite automaton, right? Meaning, so to compute this function, what do I need to memorize? I need to memorize what's the last bit that I saw. If I remember what's the last bit that I saw, then I can tell you, okay, did the string end in 1 or not, right? So I initially didn't see anything, so I'm wherever I am. I'm assuming that I'm kind of starting with 0, but if I see bit 0, then I'm going to store it as that's the bit that I just saw. If I see 1 on the other hand, I need to update my memory to say, okay, 1 is the bit that you just saw, right? So you're kind of hard coding what bit you just saw into the state. And you can do this because you're only interested in kind of memorizing a single bit, okay? So you can interpret this as the state corresponds to saying bit just seen is 0. Bit just seen is 1. Okay. Now let's do a slightly more involved example. I only want to output 1 on strings which have an alternating pattern. Okay, so for example, f of 0, 1, 0, 1, 0, f of 0, 1, 0, 1, 0, 1, 1, 0, 1, all of these things would be 1. Whereas if there was ever even a single repeated bit, I should output 0. Okay, so this is the function that I'm trying to compute. And can I design a DFA for it? Any suggestions? Again, I'll get you started and then I'll fill in. Hopefully we can figure out what the DFA should be. And again, think like what you need to memorize to solve this thing, right? There's some kind of resetting that goes on. So the only thing that I need to remember is what the previous bit is, and is it the same as my current bit? Okay. Yeah.
So you add a new building state. So whenever you see full repair, please you go to the building bit and never go.
Okay, so the suggestion is let's have a failure state where you go to if you see 2 repeated bits. And kind of, this DFA, the way we defined it, once you see 2 repeated bits, you are done. There is no hope of recovering. You should just output 0. You should just fail. Okay. So, but how do I know whether I've seen 2 repeated bits or not? We need to memorize what we just saw and then compare it to what we're seeing now. Okay. So what I can do is let me put in 2 states, call them 1, 2, 3. Again, the names of the states are not as important. If I see 0, I go here. If I see 1, I go here. It's kind of telling me, okay, this is what you saw now. And what should I do if I'm here and I see a 0? Yeah. Go to state 3. So we're thinking of state 3 as kind of the death state. You go lie in the corner there and don't do anything afterward, right? So meaning, again, these are, let me call this a dead state, because both arrows kind of point to itself. So once you reach there, you are never going to get out of it. Okay, and this is something that this idea of having dead states is very useful in designing DFAs. You'll come across them in many other examples as well. Okay. And if I'm in state number 2 and I see 1, again, I saw 2 consecutive ones, right? Which means I should reject or I should output 0 here. So once again, I go to the dead state. All right, yeah.
Why couldn't we just modify the previous example to, instead of it being 0 and 1 again, we just basically had those arrows, point those arrows to the dead state?
Well, you're saying here?
You know, like instead of the loops of 0 and 1 that go back to the same state, just send them both to the dead state.
That could also work. Yeah, it's actually what we're going to do is going to be similar. Okay, I'm just adding it one more extra state to make it a little more clear. Okay, but that's an excellent suggestion. That would also work. Okay, so if I'm in state number 1, if I'm here and I see 1, what should I do? Go to state 2. Okay, and if I'm in state 2 and I see 0, I go here. Okay, again, each state has a semantic meaning for us, right? So this is a dead state, and this is saying bit seen before is a 1. Okay, and this is bit seen before is a 0. Okay, so these are our sort of mental interpretations of what state number 1 is supposed to be and what state number 2 is. Okay, so that corresponds to seeing a 0, this corresponds to seeing a 1, and you kind of jump between them. Okay. Any other questions? So what should the accepting states be? Yeah. 1 or 2. Why not 0? So this is kind of a nitpicky convention. So when we think of 0, 1 star, it also has the empty string. Okay, it has no real impact on any computing. It's just a convention, and we have to fix something for consistency. So there's this notion of an empty string. It's like kind of like the empty set in sets, right? And 0, 1 star is also supposed to have the empty string, right? And you can debate, maybe we can have a full philosophy department debating whether the empty string has an alternating pattern of 0s and 1s or not. But let's just say it does. Let's just fix on that. So then you have to also accept the empty string. Okay, so that means I have to make the start state accepting as well. Okay. Yeah.
So then if you only have 1, if you have no empty string, it's like not alternating, right? But what if you only have 1?
It is still alternating, right? Because there are no 2 things which are the same. Again, that's a good question. Like, it's a convention that we have to fix. And the convention that we are using is that as long as no 2 consecutive bits are the same, you should output 1. Okay. Any other questions? Okay, so now let me make it maybe a little bit more interesting. Can I, okay, let me write this in English. So design a DFA that outputs 1 on strings that have the same starting and ending bits. Okay. So I only want to output one on strings where the first bit and the last bit are the same. So they're both 1 or they're both 0. Okay. So for instance, f of 1001, f of 10101. These all should equal 1. And okay. Is this function computable by a DFA? And if so, can I come up with one which kind of does exactly what I want here? Any suggestions? Yeah.
DFA design are granted to other independent DFAs.
Okay.
So one we put a case that the start is by 0 and the other is the case for starting with 0 starting with 1.
Perfect. So the idea is, so you start from wherever you were starting, but then kind of our universe splits into two worlds, right? One where the starting bit is 0 and the starting bit is 1, right? And then all we have to do is check whether the starting bit matches whatever universe we are in, right? So here, check if last bit is 0, check if last bit is a 1. Okay, but we already saw DFAs which to do that. You know, this was a DFA. We checked whether the last bit is a 1. Okay, we kind of really can just copy and paste this DFA over here. So let me do that. So I come here and if I see a 1, I stay there. If I see a 0, I go here. And if I see a 0, I stay there. If I see a 1, I come back. Okay, so this is just the DFA that we had earlier for recognizing strings where the last bit is 1. Okay, just kind of, you know, change where the arrows are coming from. And we can kind of copy the same idea here. So if it's a 0, I stay here. If it's a 1, I hop across. If it's a 1, I stay here. If it's a 0, I come back. Okay. So the bottom part is really trying to memorize, you know, what's the last bit that you saw. Both are doing kind of the same thing. What's the last bit that you saw, but they're prioritizing one bit over the other. Okay. So the top one is checking is the last bit 0. Okay. So what should my accepting states be? Yeah. 0, 2, and 4. The most important ones are 2 and 4. 0 is again to get the empty string in it. It's kind of a convention. Okay. So if you look at this diagram, you can check, you know, what happens if I pass 1, 0, 0, 0, 1, 1, 3 zeros and 1, right? I start here, I go here. Now I see a 0, I go there. I see a 0, I'm here. I see a 0, I'm here. And then I see a 1, I come back. Okay. So once our universe split, all we had to do was memorize the last bit. Okay. So it always helps to think about it in this semantic sense. Like, if you're trying to design a DFA, which is something you'll come across not in this class, but also in some compilers courses as well, to just really kind of think about it verbally, like, okay, what do I need to remember? You know, can you think of it as splitting up into subtasks? Okay. Any questions about this construction? Yeah. Right. So that's an excellent question. So if you had to remember, like, in some sense, remember k bits, then you might have to need 2 to the k states. And there are ways of addressing that. We'll talk about that in the next lecture. Okay, again, just as for circuits, we were wondering how many gates you need. At some point, we'll also ask how many states you would need, or is it even doable with the DFA and so on. Okay. Any other questions? Okay. So, I don't want to go into more and more examples. We'll come across more of them in when we're doing more complicated constructions. And the TS will go over more examples in discussion sections. The text has several ones. And if you have access to it, Sipser's Introduction to Theory of Computation textbook is an excellent resource for finite automaton. In fact, I think it's a better resource for DFAs because almost the first half of the book is devoted to that. Okay, but DFAs we are not covering it too much depth. All right. So we saw some examples. Let me distill some of the things in the definition of the DFA, right? So whenever you think of a DFA, certain things are fixed or are bounded. So what are fixed? The number of states. Okay, which for us is the number C. Okay, bounded meaning is something that doesn't change with the input length. So the transition table is also fixed. Okay, and the set of accepting states S. Okay, and the input length, of course, is unbounded. And in terms of notational convenience, double circles denote elements of S. Okay, so if you go here, the number of accepting strings is more than 1. Accepting states, sorry, is more than 1, right? So here S is supposed to be 2, 4. Okay. Is there a question? Yeah, input string is finite. Yeah. So input string is finite, but you can think of the description length as being 100, but you can run it on strings of length 1,000,000, 1,000,000,000, 1,000,000,000, doesn't matter. Okay, but it has to be finite. Okay. And so DFAs are also called finite state machines. Okay. And sometimes you'll see a different description of these machines. So let me just put a translation index for what we are doing and what you might see in other places. I write what these things are and then kind of write down the dictionary. So Q is supposed to be the set of states. Okay, so it can be any finite set. And for us, it's just the set 0, 1 through C-1. Okay, So we are adopting the convention that the states are just going to be labeled as numbers from 0 to C minus 1. But realistically speaking, it doesn't matter what you label them. The function computer will not change as long as the markings and diagrams carry over. Okay, it's just like whether you change variable, what variable names you set doesn't change what function you are computing. Okay, and sigma is called the alphabet. As I said, we are only looking at strings over 0, 1. Okay, so just binary strings. But you can imagine, automata which takes strings like 0, 1, 2 star. Okay, so then you'll have to add an arrow for 2 and so on. But we are interested mainly in the model of computation. So it's a complexity that we can easily do without. And this is the transition function. S0 is the starting state, which for us is always the state 0. Okay. Again, you can specify it to be something else, but we are adopting this convention. So instead of specifying 5 things, we just have 2 things to specify. Again, S is the same. It's just the set of accepting states. Okay. So if you see, different definitions somewhere else, don't get confused. It's really the same. What we are doing is just a little bit more streamlined. Okay. Any other questions? All right. So there's also one other language for talking about DFAs. So we are talking about functions, really, like, we are always interested in computing a function. Okay. But another way to describe a function is to specify the language computed by the function, which is a set of all strings x such that f of x is 1. Okay. So sometimes people talk about what language does the DFA compute? Okay. I have a language. Can you design a DFA which computes this language? Okay. It's just the same thing. You're specifying, either you're specifying it as a function or you're describing the function implicitly as a set by specifying which strings are making your output 1. Okay. And you might also see things like, DFA D computes function F. Might also see something like DFA D Okay, so we already saw what it means to say a DFA computes a function, right? So the DFA should output 1 if and only if the function outputs 1. We say the DFA computes the language L if and only if the DFA says 1 when the string is in the language and it says 0 otherwise. Okay, you can think of it as a verification algorithm, right? Imagine you have a DFA for correct English language sentences, right? So then basically I'm checking whether the sentence is grammatically valid, is part of the language. That's kind of where this originates from some parts of linguistics. And people also say D recognizes language L. All are equivalent forms. By and large, we'll stick to the notation that we have functions that we're trying to compute and nothing else. Okay. Yeah. What do you mean, one or more conditions?
Like implicit in D of X, like it kind of, I guess it's like a turtle and or like chicken and egg problem that they return 1.
So there's a difference here that we think of languages as coming first, right? You have a function, something specified to you, and then I'm trying to design a DFA for it. Okay, in the same way, someone gave you a language. So here's a language, the language I'm interested in is all strings X, where the first and last bit are not the same. Okay, maybe someone told you that. That's the language I'm interested in. Then you can ask, okay, is that computable by a DFA? Is there a DFA that can recognize this language? Okay, so like for any language, there may be multiple DFAs which either recognize it or compute it. Okay, so we think of the language or the function as the specification, the DFA as the implementation, as a implementation if it exists. Okay, any other questions? Okay, now that we have these ambiguities in notation and language set aside, let's stick to functions and computing functions. Okay, and one thing we're going to look at, not just here, but in almost everywhere, is to ask meta questions, right? And we saw it even with circuits. We saw something called syntactic sugar, right? Somehow you could compute one function, then you could use that as a piece to compute other functions, right? You can group functions together, okay? Can we do similar things for DFAs, okay? Can we somehow compose functions computable by DFAs, once again, using just DFAs, okay? So can we perform operations on functions computable by DFAs? Okay, so there are various operations. Some we already saw, which are important, and some which are particularly important in the context of DFAs and its applications, as we'll see in the next couple of lectures. But first, let's talk about a natural operation that we think of on functions. We saw it even several lectures ago. Suppose I have a function f1. Okay, this is computed by DFA D1. Okay, I'm telling you that function f1 is computable by a DFA. Function f2 is another function that is computed by a DFA D2. Can you tell me something about the AND of the two functions? Okay, I want to be able to compose functions, perform operations on functions. So one simple operation, of course, as we saw, is the AND operation. You can ask AND or not. Somehow, like, can we at least perform these meta operations and things that you're already computing? Okay. So kind of, we have bigger Lego pieces now. Can we put them together? So let me define a new function now. So f of x is f1 of x and f2 of x. Question. Is f computable by a DFA? Okay. Okay. So let's take a 5-minute break, and when we come back, we'll talk about this question and other ways of composing functions while staying within the same model. Okay. Okay, so we're asking, are DFAs kind of closed under this AND operation? You have something that is easy enough to be computed by a DFA. What happens when you do the AND operation? I mean, some of these things are trivial when you think of programming code, right? Let me just do the silliest programming example. If I have some program for computing F and G, how can I compute the AND of F and G? I'll say, okay, write A as compute A, which is F of X, B, which is G of X, and then return A and B. Okay. And we said, okay, one way to interpret DFAs is that they are algorithms which are single pass and constant memory, right? So what I wrote down here is still constant memory. If F and G are using constant memory, I'm kind of, maybe just adding 2 extra bits to it, so nothing is changing. But can this lead to a DFA? Yes or no? Any guesses? Can I build a DFA out of this?
Sure.
Right, but there's a problem, right? So we said DFA gets to see each bit only once. But what's happening here? It's not a single pass algorithm, right? So you're computing F by reading all of the bits, but then you can't go back. So DFA, by definition, can only see each bit once, right? So if someone told you, tell me whether single pass constant memory algorithms are closed under and seems somewhat tricky now, right? Because I can't just say compute F and then compute G and then do the AND, because you only get to see the data in a streaming fashion, 1 bit at a time, and then you can't go back. Okay, only one shot at each bit. Okay, so this is not a single pass algorithm.
And DFAs are limited to single pass?
Yeah, DFAs are always single pass algorithms. Okay, so you can think of DFAs pretty much, they're essentially equivalent. There are some maybe minor technicalities that you should sweep under the rug. The DFAs are essentially equivalent to single pass constant memory algorithms. Okay. Whereas when you do this AND, it's not single pass. So doing these compositions while still being single pass is kind of tricky and would be a useful tool. You can imagine this being useful under various systems. Okay. As an example, so let's say DFA that, let me add one other sort of notational convention. If D of X equals 1, we say D accepts X. Okay. So if you have a DFA and an input string on which the DFA outputs 1, sometimes you'll see this phrased as saying, okay, the DFA accepts the string X. And if D of X equals 0, then D rejects X. Okay. Because I mean, some sense in many applications, DFS are used as filtering tools, especially if you have some inputs that you're entering into some command systems, then DFS is used as to check input formatting and so on. So it accepts or rejects the input. Okay. It's the same thing. So suppose I have a DFA D that accepts strings X that have an even number of ones. Okay, and similarly, I have a DFA D2 that accepts strings that have a multiple of 3 number of ones. Okay, so the first DFA is computing whether or not the number of strings, number of ones is divisible by 2. The second DFA is computing whether or not the number of ones is divisible by 3. What would the AND of the two compute? Yeah, so accepts X that have a multiple of 6 number of ones. Okay. So how can I design a DFA for the AND operation? Maybe this example, if you think about it a little, it might suggest a way forward. But let's keep that just in mind, and we'll see the general solution and then come back to it. Okay. Let me say that, having this closure under AND operations is somewhat delicate. For many computational models, it is true that, something is computable. If F is computable in the model and G is computable in the model, then AND is often computable. But there are some cases where it's not. Okay, so it's not always immediate. So let's start with what we have. We have a DFA, D1, that computes F1. Okay. Maybe it has C1 states, and the transition function is T1. The set of accepting states is S1. Okay. We have a DFA D2 that computes F2. Maybe it has C2 states. It has a transition function T2 and accepting states S2. All right. And we want to know, is F1 and F2 computable by a DFA? Right? How can I compute the AND while still doing a single pass over the algorithm, right? Over the input. That's what we want. Any suggestions? Yeah?
Of a DFA with C1 and C2 state.
Right. So again, always think like a DFA, right? Somehow, what do you need to do to compute the AND? Pretty much, we don't have any knowledge about what D1 and D2 are doing. So we want to be able to simulate D1 and D2 at the same time, right? So you want to kind of run parallel simulations of D1 as well as D2. So let's do that. Let's just keep 2 separate memory banks in our mind, where one memory bank is kind of simulating the first automaton. The second memory bank is kind of simulating the second automaton, right? So we said, okay, think of a DFA as you have some circles and there's a person jumping around them. Now I have 2 persons. I kind of split myself into 2. They're hopping on the 2 DFAs in parallel, okay? And when I do this, I could still maintain the single pass, right? Because I see a bit, both of them take the jump. Okay, so that's all. At the end, I'll make a decision based on where they end up, but at least the simulation will be fine. So the idea, run D1, D2 in parallel. Okay, I'll elaborate on this in a second. So the number of states that we have for the new automaton C will be the product of these 2 states, okay? And for simplicity, I'm going to slightly violate your convention here and identify these states as pairs I, j. Now I said states should always be numbers from 0 through C minus 1. But the names you give is not particularly important. That was easy to make the definition crisp, but it doesn't change how I label them. Now I'm going to label the states with pairs. So every state has 2 numbers written on it. Okay, you should think of it as a grid. Okay, so the states that I have are kind of occurring in a grid. So this is C1. This is C2. Okay. So this is like, maybe 0, 0, 0, 1, 0, C2 minus 1, 0, 2, 0, so on. Okay. The states are kind of elements of this grid. You should think of the rows as corresponding to you have C1 rows corresponding to the first automaton, then you have C2 columns corresponding to the second automaton. All right. So these are the states, and how do I define the transition function? So here drawing the diagram would be somewhat tricky, so let me just define it formally. So the transition function should be something that takes the state space times an input bit and outputs a state, right? So in our case, it's going to be something which takes a pair of indices, I, j. I is meant to mentally denote what state your first automaton is. J corresponds to what state your second automaton is. Right? And then outputs a similar pair. Okay. We are almost done. So what should I do now? So T, let's say I am at state I, j, and I see a bit A. What states should I jump to? Any suggestions? Again, remember, we're really trying to mimic both of them in parallel, right? Yeah. Yeah, exactly. So let's use the transition functions of the individual automaton, right? So I have 2 people doing the job for me. The first person jumps according to the first automaton. The second person jumps according to the second automaton. Okay. So kind of the first coordinate is updated according to the first automaton. The second one according to the second automaton. Right? So the important thing is that this is T1 and this is T2. Any questions about this? Not necessarily. I mean, you're blowing up the space, so they're kind of really just doing everything possible for implementing both machines at the same time. Okay. And the only thing that we have to specify is a new set of accepting states. So what should the new set of accepting states be? Any suggestions? Yeah. Yeah, exactly, right? So the suggestion is look at states where the first person says, hey, I ended up in a good accepting state. And the second person also says, I also ended up in a good accepting state. So only when both of them say yes, you have to output yes, right? So this corresponds to saying, look at all pairs where the first coordinate is in S1, which makes the first machine accept, and the second coordinate is in S2, so that the second machine also accepts. Okay. So that's it. And this new DFA computes D1 of X and D2 of X. Okay. So even though when we thought of it as a simple program and we said, okay, compute f of x and then compute g of x and then output and, it violated this single pass property that was so important to us. By kind of implementing them in parallel, we are able to maintain the single pass property. Okay. It came at some cost. What's the cost? We had to blow up the memory. Okay. We had to blow it up multiplicatively. Okay, if the number of states was C1, the number of states was C2, the new number of states is C1 times C2, which again, I think makes some sense. If you think of it in terms of bits, it's really like addition in terms of the number of bits required, and it's necessary. Okay, any questions about this construction? So we now know that at least DFAs are kind of closed under ANDs, meaning if something is computable by DFAs, if two functions are computable by DFAs, and the AND is also computable. Okay, so let me state that as a theorem. DFAs are closed under ANDs, meaning implies that AND is computable. Okay. And let me just also rephrase it in the language of languages. So let's say I have language L1 and L2. These are recognized by DFAs. Meaning, there's a DFA which only accepts strings which are in L1, and there's a DFA which only accepts strings which are in L2, right? So when we talked about functions, we said that we were trying to compute the AND, but in terms of languages, what's the corresponding operation to AND? Intersection. Okay, so again, it's just stating the same thing in two different ways. Then there is a DFA that recognizes or computes L1 intersection L2.
What is L1 and L2 then?
These are the two languages which are computed by DFAs, right? Again, so just to reiterate, a language is recognized if the DFA outputs 1, if and only if the string X is in L1, right? When we're doing the AND, we're doing the exact same thing. We want to check if the first one says 1 and the second one says 1, which corresponds to taking the intersection operation on the corresponding language. Okay, yeah. Yes, exactly. So that was going to be my next question. So you jumped ahead. So let me identify this excellent point. That wasn't a planted question. So what about OR operation? Okay, what if I tell you, there's a DFA that computes F1, DFA that computes F2. Can I compute the OR of the two things? Okay, And so as we said, we really are going to mimic the two automaton. So we kind of follow the same construction. Everything stays the same. So let me just write it down. So states, the new states is C1 times C2. And the transition function is the same. So I can copy it. Okay. So the difference though is now we only require one of the two automaton to say one. Okay, so you have two people kind of jumping on hoops for us. And as long as at least one of them says, hey, I'm in a good state, we have to output one. Okay. So the only thing that needs to change is the set S. So what should the set S be now? Yeah.
Should be like IJ, but then I could be in C1 and J in S2, or and then union that.
Yeah, exactly. So let me just write it down in a slightly different notation to what you said, which is either the first coordinate is in S1 or the second coordinate is in S2. Okay. What you said is basically take S1 times C2 and C1 times S2, which is exactly the same. Okay. Any questions about this? So just by changing the set S, but keeping the same transition function, we're ending up with a different operation that we can perform. Okay. Any questions? All right, finally, so let me copy this stuff too. So we just saw that this is closed under ORs as well. So if F1 and F2 are two automaton that are computable by DFAs, then their OR is also computable by DFAs. Okay. And in the language of languages, this corresponds to, OR corresponds to what operation? Union. Okay, so you're checking whether, okay, is the first automaton saying one or the second automaton saying? Okay, so is X at least in L1 or is it in L2, which corresponds to taking the union? Okay. Any questions about this? Okay, so we saw two operations which you can perform on DFAs while still being within the class of DFAs. Maybe we're losing something in memory, but we're still staying within single pass and constant memory. Right, C1 and C2 are constant, C1 times C2 is also a constant. Okay. There's one other Boolean operation that we saw last class. I mean, not last class, but a couple of classes ago. So let's revisit that. What is that operation? Well, what about the not operation? Okay, so suppose f is a function is computable by DFAs. Okay, is the negation of f. Let me write it as f bar. is the complement of the function computable by DFAs. Okay. So like, some sense we saw DFAs that can check whether the number of ones is divisible by 3. What if I wanted a DFA that checks whether the number of ones is not divisible by 3? Can I do this also by a DFA? How? Any suggestions? Yeah. Okay, so you can just change the set of accepting states. You don't need to change the transition function, just flip S, right? Again, it's essentially what the memory is saying, asking you to do, right? So if you mimic your original function, original DFA, you ended up in some state at the end. If that was an accepting state, you were originally saying 1, now you should say 0, right? So you just flip the set of states S. So idea. So suppose D computes F and D is defined by transition function T, set S, and has C states. I can define D bar as the same transition function, but take the set of accepting things to be all things which were not in the original set. Okay, so this is the complement. Okay. Any questions on the claim? Okay, so now we have OR, AND, and NOT. So you can imagine, you can put these things together as long as you have some constant number of OR, AND, and NOT gates, ways of putting things together, you'll stay within the class of DFAs. Okay. Again, as I said, one thing we should always strive to do is to kind of build pieces that you can reuse, which is what these properties will allow us to do. Okay. Any questions about this? All right. So now what we're going to do is ask a couple of questions which will lead us to one of the biggest leaps in theoretical computer science. And we'll ask it again in the context of performing operations on functions or languages. Okay. So we're studying what I call closure properties, right? So if F and G are computable by DFAs, their AND is computable, their OR is computable, and their NOT is computable. So, their compositions are also computable. Like if I have 3 functions, F, G, and H, they are computable by DFAs. Okay, so question. Something like this computable by DFAs? Yes, right? Because we know there's something which computes F and G, and then I'll take that and then the OR of this. Okay, so you can put these things together and nothing really changes from the aspect of being computable by DFAs. Okay. But here's another operation which is very important when you think of recognizing patterns, right? So one of the main uses of DFAs, although this is something that we haven't yet seen, and we'll see it in the next lecture or the lecture afterward, is that DFAs are really useful as tools, as succinct tools for recognizing patterns. In fact, if you think of their real utility in computing, in practice, they're mainly used for this purpose. loosely speaking, they're good for recognizing patterns. Does my string X have 0, 1, 0 somewhere within it? Does my string X have alternating ones and zeros? Does it have the same first and last bit and things like that? Okay. And one operation which is important in this context is what's called the concatenation operation. Okay, as an operation, this is more intuitive from the perspective of languages, but let me state it first in terms of functions, and then I'll also talk about languages. Okay, so let's say f comma g are functions on bit strings. Boolean functions, meaning they output zeros or ones. The concatenation of f comma g, which will denote as f little circle g, is a new function that we are going to define. And say the concatenation outputs 1. Okay. It's 1 if and only if I can break up my input string into 2 pieces, where the first piece should make the first function output 1, and the second piece should make the second function output 1. Okay. So if I can write x as x1 and x2, where f of x1 is 1 and g of x2 is 1. Okay, I should be able to split my string into 2 pieces, where the first function says 1, and then the second function says 1. Okay, says in terms of languages, if I have 2 languages, L1, let's say LF and LG, then the language of the concatenated function is just the concatenation of the 2 languages. Again, it's just defined as all strings x, such that x equals x1 concatenated with x2. This is in the first language. This is in the second language. Yeah.
Why is it important to distinguish languages if we're only really ever going to do a binary?
What do you mean distinguish languages?
The language we're talking about is binary.
Mm-hmm.
And so if we have 2 languages and they're both binary, why is it important that we identify them as 2 different languages?
No, they can be very different languages, right? So like, for instance, one could be all strings which have an even number of ones.
Oh, okay. So
right. The other could be all strings where it doesn't, maybe divisible by 3, right? Or divisible by 10. Okay. Yeah. So yeah, that's a very good question. So we are not concatenating the outputs. We're just think of it as kind of verifying stuff, right? So F is checking for some conditions and G is checking for some condition. So F evaluates to 1 if X satisfies some conditions. G evaluates to 1 if X satisfies some other conditions. Okay, the input satisfies some conditions. We're saying, can I break up my input into 2 pieces, where the first part satisfies my first requirements, the second part satisfies my second requirements. Okay, you can also define concatenation in terms of the output, but it's more non-trivial when you think of it in terms of the input. Okay, yeah. Yeah, it's arbitrary. So as long as there's some division which makes it happen, we are happy. Okay, it doesn't have to be in the middle, doesn't have to be kind of, the last button or anything like that. As long as there's any division which makes it happen, we are happy with it. Okay. So let me just state an example. Suppose f was a function which checked okay. So f of x is 1 if x has 0, 0 somewhere within it. And maybe g is a function which says okay. So g is checking, does my input have 1, 1 somewhere within it, right? 2 consecutive ones. Now f circle g, the concatenation, what would it compute? It's essentially checking if there is a 0, 0 in your string, which then gets followed by 1, 1, 1 somewhere. Okay, it doesn't have to be immediate, but it should happen afterward. Okay, so 1 if x has 0, 0 somewhere and a 1, 1 after this 0, 0. Okay, does it make sense? Any questions? So in terms of closure operations, one thing we can ask is the same thing that we've been asking before, right? If f comma g are computable by DFAs, is f circle g computable by a DFA? Okay, and answering this question will lead us to kind of really understand the power of abstraction, as we will see. But first, again, let's start with thinking of this in terms of programs, right? So suppose I ask you, okay, write me a program which can compute this concatenation. I give you some black box, some kind of library which computes f, some library which computes g. Can you write me a Python program which computes their concatenation? Okay, let's just do that as an exercise. If we can't even write a program, then we should be even more worried. Okay, so let's say def f concat g of x. Okay, so what can I do? Any suggestions? I'll again, don't bug me about the potential bugs in the border cases. So I'm just going to write something which is going to ignore some border cases, but let's not worry about that. Now, for all possible ways of splitting the string x, I have to check something, right? Compute a, which is f of x0, x1, all the way up to xi minus 1. B, which is g of what follows. Okay. You would use list comprehension for either of these things, but let me not stress that because that's not important. And you say if A equals 1 and B equals 1, would return 1. Okay. So you're really checking all possible ways of splitting up the string. Okay. And if none of them work, you would return 0. Okay. This is how you would write a program for it, right? You know, if I had to compute the concatenation, I would just enumerate over all possible ways of splitting the string. Yeah. Yeah, no, it's not. As I said, you know, I'm ignoring some border cases because then I have to write a case analysis, kind of identify the I equals 0 and length case should be separate cases. Okay. So this is ignoring the empty string for now. Okay. It just amounts to adding an extra case for the borders. Okay. But now if you think of this as an algorithm, this is far from being a single pass algorithm, right? It's making n passes over the algorithm. For every possible split, you're doing a pass. I'm checking, okay, for the first split, I check the first pass is, okay, split it into x0 and everything else. The second pass says do x0, x1 and everything else. Okay, I'm doing kind of an unbounded number of passes over the input. But when we talk about DFA, we were asking, can you do it with a single pass still? Okay, doesn't that seem very tricky? Okay, so let's at least do, you know, kind of one example. So let's take this case. Oh. Let's take that example and play with it a little to kind of get some intuition about concatenation. Okay. So let's say playground. Let's try what happens for that specific example, just to get some intuition of what we need to do. Okay. So f equals 1 if and only if x has a 0, 0 in it. Okay, so for instance, if I have 1, 0, 1, 0, 0, 1, then f evaluates to 1. Okay. On the other hand, if I just have 1, 0, 1, 0, 1, 1, 1, or f of 0, 1, 0, 1, 1, 0, this should be 0. Okay. And the other one was just, does it have a 1, 1 in it? Okay. So, you know, let's at least make sure that this has a DFA for 0, 0. Okay. So what's a DFA for computing a string, whether a string has a 0, 0 in it? I'll start with, you know, this, and I immediately start keeping track of what I see, right? And if I see a 0, then I need to check if the next bit is a 0. Right? If I see a 1, then I don't make any progress. So that's what I'm going to do. If I see a 0, I go to this new state. If I see a 0 here, then I've hit my jackpot, kind of jump across. Okay. If I see a 1, no progress, I just stay here. If I'm here and I see a 1, what should I do? Go back to 0. Okay. And once I get here, I don't need to worry about anything else. I saw a 0, 0, I'm happy. Okay, so this is my accepting state. Okay, so this is a DFA for F.
Pictorially, how would you show, if you were composing DFAs, how would you show the connection from this to the next one?
Well, we don't even know how to compose, but you would probably just relabel the nodes so that there's no overlap in the names and then draw arrows. Okay, I think pictorially that's what you would do. So let's draw a DFA for G now. It's kind of really the same thing, but the roles of zeros and ones is flipped. Okay, so if I see a 1, I made some progress, I go to the next node. If I see a 1, I make some progress, so I go to the next node. Okay, if I see a 0, nothing doing. And if I'm here and I see a 0, I go back. This is a DFA for G. Okay, so now let's just play around, right? We have these two DFAs, one for F and one for G. Is there some way to put these two together to try and get a DFA for the concatenation? Okay, any suggestions? Yeah. Oh. It doesn't have to be immediately. Yes, because that's a good question. So in a definition of concatenation, it doesn't have to be immediate, right? So as long as 0, 0 is followed by 1, 1 somewhere afterward, we're happy. It could be after 10 other bits, 100 other bits, we're okay. Okay. Yeah. Right. So let's try that.
To be clear, if we were like to reverse that, it would also be reversed. It would be 1, 1, and then a 0, 0 followed somewhere after the.
Yeah. Okay. So the first suggestion I got was, maybe you should just kind of put arrows from here to here. Okay. So let's try that. And maybe I'll just copy it instead of erasing it. Okay, the suggestion was, maybe let me give some new names to these things, these states, so that there's no confusion in 0, 1, 2. They're kind of two different things. And said the suggestion was, maybe just point things from the second accepting state to the next string. Okay. Does this work? Does this work? Yeah. So are you trying to optimize, or are you trying to, well, let's first see if this works, and then we can try and see if we have to fix it or we can optimize. Okay, would this work or not? Yeah. Exactly, right? So it's going to miss a 1, 1 pair, because somehow if I see a 1, if you see 0, 0, 1, 1, right? You see 0 and 0, you end up here. If I see a 1, I'm going here, and then I see a 1, I go here. So I haven't reached this state. So what would be a fix for that? Yeah. Yeah, so we can do this. Okay, maybe let me draw this with a new color to signify it's a new arrow. Okay. Yeah.
the other?
2 or 0 prime with the other. That could also work. It's kind of optimizing one more state. But this is, I think, conceptually a little easier. Okay, but I think you can also make that suggestion work. Okay. Any questions about this? So again, so my claim is, so now what's going to happen, right? Until you see a 0, 0, you're never going to see 2. And from there, if I see a 1, 1, I'm just kind of going to accepting state. Okay. So for this specific case, we are able to get an automaton for computing F circle G. Okay, yeah. Yeah, so I'll get to that in a second. So this idea of linking the accepting state of the first automaton somehow to the start state of the second automaton worked in this case. And one reason it really worked is because these automaton were simple enough. Like the accepting state was kind of like a semi-dead state. It wasn't doing anything interesting once you reached there. Okay. Whereas if you had other automaton which counted the number of ones being 2, being 0 mod 2, okay, then this construction would not work. Okay, so let me give this as a puzzle for you to think over. And then we'll see what to do in the next lecture. So f of x is 1 if number of ones is divisible by 2 and g by maybe, let's say, 6. Okay, so what if I have something like this? So I want to check if my string can be split into 2 pieces, where in the first piece, the number of ones is actually even. And in the second piece, the number of ones is divisible by 6. Okay, so then this link up strategy would not work, at least not straightforwardly. Then you have to be somewhat clever about it. Okay. In the next lecture, we'll try and think about this a bit more. But really, the very surprising thing is that this is even possible, as we will see, while staying within DFAs. Okay, you can do it with a single pass, no matter what.
So